everyone. Welcome to re:Invent 2023. Thank you for attending our session today. I'm Taiji Iwai, Senior Solutions Architect from AWS Japan, working closely with Nintendo and Nintendo systems. Today, we are thrilled you are joining us to learn about a Nintendo systems modernization journey. And as you know, Nintendo eShop is a web-based worldwide e-commerce service powering over 120 million Nintendo Switch users. In this session, you can learn about the Nintendo eShop backend infrastructures and development teams, as well as its history. Additionally, as a part of modernization journey, we will introduce platform engineering, which has gained popularity in recent years. And we will explain how it can be implemented through a combination of AWS services at 100 million user scale. So this is agenda. To start, we will introduce an overview of Nintendo eShop, how it has evolved on the backend architecture to improve agility and go-to-market speed, and also explain why we decide to modernize the entire backend of Nintendo eShop. Next, we will discuss how Nintendo eShop transitioned into microservices architecture, and we will explain how we decouple the monolithic system into discrete microservices, and how our engineering teams are structured around them. Then, we will introduce how our platform engineering work has addressed and overcome the common challenges with microservices architecture. This will include the detail on the specific technology choices we made to implement platform engineering successfully. As a practical example, we will showcase the launch day system performance for very major, highly anticipated game title recently released. And finally, as a future of Nintendo ecommerce service, we will introduce plans to expand Nintendo eShop into wider API platform service. With that, I will hand it over to Shinya from Nintendo Systems to explain this splendid customer journey. So please welcome Shinya.
Thank you, Taiji, and good morning, everyone. My name is Shinya Ogura, and I'm a manager at Nintendo Systems, and I've been working on developing and operation of Nintendo's network services for more than 10 years. In the most recent 2 years, I've been managing the Nintendo eShop server-side team for about 2 years. So, what do we do at Nintendo Systems? At Nintendo Systems, we develop and support various network services that makes the gamers, players' gaming experiences more rich and enjoyable. One example is a game server that provides several online features to the game titles. And Game News is a place where you can discover various information of the game titles you are interested in. And of course, Nintendo eShop is a place where you can browse and purchase digital softwares. These are just a few, and there are many other services that we manage. But if you are interested, you are always welcome to purchase your Nintendo Switch and try them by yourself. So let's get into details of Nintendo eShop. So Nintendo eShop is an e-commerce service for Nintendo's gaming devices, where you can browse and purchase these game titles. Many different features make up what we call eShop. For example, we provide product catalogs for the users to browse the products, and we provide various payment methods for you to deposit value into your Nintendo eShop balance. And with the balance, you can purchase or redeem game titles. And then our system distributes digital contents of the purchased game in a format of encrypted binaries. And finally, the DRM functionalities allows the players to play the purchased game. So Nintendo eShop for Nintendo Switch is a web-based application. And it actually isn't very special on how it's built. Its front end is a web-based, is a single-page application built on React, and it runs on the built-in browser of Nintendo Switch. And like the most SPA application does, the browser executes the JavaScript code to send a request to the REST backend systems. The backend system of Nintendo eShop consists of multiple applications where we implement core business logic and store valuable data. And Nintendo eShop is a global 365 service, and currently we serve over 40 countries with over 20 currencies against 120 million Nintendo Switch units around the world. As for the amount of data, our system has over 500 tables with 100 million account records and over 3 billion transaction records. Nintendo eShop has been in service for more than 10 years, starting from Nintendo 3DS in 2011. And over these years, Nintendo's digital sales has grown significantly. Between fiscal year 2017 and 2023, the digital sales has grown more than 10 times. And the ratio of digital sales against the total sales has also grown to just under half. And as the digital sales grew, our system had to deal with three things that kept growing: growing number of accesses, growing data size, and the growing number of feature requests from the stakeholders around the world. So we have been continuously refactoring the system to deal with this business growth and to adopt the new technical trends. The refactoring of the Nintendo eShop system took place in three phases, which are on-premise, migration to AWS, and modernization. So the first phase was on-premise. When we first launched Nintendo eShop in 2011, all the system components were deployed on the on-premise infrastructure, which is managed by our colleagues in the US subsidiary. The core application server and database were monolithic, and the application was built using Java and Tomcat. As more 3DS were sold and the digital sales grew, we needed to address many non-functional requests for ever higher availability, scalabilities, performance, audit requirements, and securities. In addition to strengthening the system, we also had to deal with continuous number of feature requests. So to cope with the growing demands and to support the business in the long term, we have decided to migrate the system to AWS. The very initial service on AWS was built on single AWS account and single VPC. By migrating to AWS, we were able to achieve agility on the infrastructure development and modifications. Also, we were able to gain scalability to cope with the traffic of the busy season and events. And to meet the continuous request and to support the new Nintendo platforms, we have implemented numbers of new application servers. The core application servers were built exclusively for each Nintendo platform. For instance, we have application server for Nintendo 3DS eShop, while there's another application server for Nintendo Switch eShop. Though the applications were separate, most of the applications shared a single Oracle database schema to share data models among the applications. And as Nintendo Switch launched and the digital sales and the functionality it set grew, the size and the complexity of the core application server became an issue for us. In other words, the complexity of the application and the database made it difficult for us to scale productivity with more engineers. In addition, the testability of the application was low, which made us rely on manual regression tests to ensure the system's quality. And as the number of application servers increased, we also began to realize the pain points of distributed monolith. Since multiple applications shared a single database, as the number of connections increased, the size of the RDS caused the scalability to hit its limits. In addition, the timing of the release must be coordinated among multiple applications, which increased the cost of the release. As a result, a major feature release was deliverable only every 3 months. All the while, the demand for new features such as Nintendo Switch Online kept growing. So in these circumstances, we have decided to modernize the system to achieve agility for timely feature enhancements and long-term maintainabilities. To modernize the system, we have devised 3 strategies. The first is well known. Splitting the monolith into microservices is a standard play when refactoring a monolithic system. And to make the most of microservice, we chose to engage in platform engineering. The platform engineering brings self-service capabilities and mitigate the cognitive load of developers and operators. And thirdly, e-commerce API platform. As the number of Nintendo's consumer touchpoints increases, so does the demand for our e-commerce APIs. So to meet the demands, we are considering offering the functionalities of our refactored system as e-commerce API platform. So first I'm going to talk about microservice. But as you know, microservice is not the only way to refactor a monolithic system. So to start with, we have compared microservice to a modular monolith. With microservice, each service can be developed and deployed independently. And each service can utilize the technologies that best suit the service. The team may choose DynamoDB or RDS or Redis, depending on the data model or expected traffic patterns. On the other hand, there's a difficulty in defining a boundary to make the services loosely coupled. And we need to be extremely careful when defining this boundary, or otherwise we will end up where we started, with another distributed monolith. In comparison, modular monolith is an architecture style where you split the internal architecture of the application into multiple modules. It's all about the internal structure of the application, so you can reuse the development or the deployment processes of your existing applications. With modular monolith, each module can be developed independently. though it requires effort to keep them independent. Because the communication between the module is just a method call, there's a lower complexity than the systems based on the microservices. But on the other hand, since it is still a monolithic application, it requires big effort when modernizing the architecture or technology. And this is a large part of why we felt this strategy will limit our future technology choices. So as a result of a comparison, we have decided to refactor our system to microservices. And these are the four major benefits that we aim to gain. The first is long-term maintainability. As mentioned before, the Nintendo's digital business has grown significantly in this decade. And hopefully, it'll continue for another couple of decades. So to support the long-term business, we believe it is essential to adopt and replace the components with new technologies. The second is improve productivity. We want to make the productivity scale as the team grows. And to do so, we want to minimize the responsibilities of the service to minimize the required domain knowledge when a new engineer joins the team. The third is shorten the release cycle. We want to deliver the new functionality or a fix as soon as possible without waiting for our next major 3-month release. And lastly, cost-effective scalability. We want the necessary part of the system to be scaled, not the entire system. And while we aim for these gains from microservice, we are aware that it's not a silver bullet. And there are numbers of pain points. We are working on platform engineering to mitigate some of them. But before going into platform engineering, I would like to talk about our approach in defining the appropriate boundaries between the microservices. Initially, we follow the single responsibility principle when decomposing a service from the monolith. That is, the responsibility of each service should be minimized with independent data and functionalities. We started by fairly simple and easy to split features, such as the management of Nintendo eShop balance and transaction histories. The major responsibilities of these services were to manage its own database and provide APIs to refer or update the data. We have developed numbers of new microservices following this principle. But as the time passed, we found this principle introduces new problems for us. We found it was difficult to estimate the total number of microservices we have to develop or operate in order to refactor the entire Nintendo eShop system. Because the number of microservices our team can handle is of course limited, it was important for us to estimate and control the total number of microservices. And when we think about incremental migration to microservice, I think we all tend to focus on simple and easy to split features. At Nintendo eShop, the difficulty was that there were not so many simple features that were easily decoupled from the monolith. The majority of the data and functionalities were complicated, and it was soon difficult for us to define microservice boundaries that would be effective and maintainable. So we made a course change. Our alternate approach was to follow a principle of domain-driven design. Before decomposing into more microservices, the overall data and functionalities are divided into numbers of domains. Our domains include products, order management, user asset management, and so on. And next, we implement the functionalities within the domain as a realistic number of microservices. This hierarchical approach, microservice approach, allowed us to estimate the overall number and the granularities of the microservices. In other words, the degree of decomposition can be adjusted according to the size of the team that is in charge of the domain. So next I'll talk about our microservice team structure. Historically, our service was developed by one set of engineers and is supported in operation by a second set of engineers. That is the developer role and DevOps role. We explicitly separated these two roles, mainly due to the compliance and governance requirements that arose with our digital business growth. The developers were granted unrestricted access to production AWS account and had to request to DevOps engineers for deployments and any infrastructure modifications. We continued with this structure when we started the decomposition of the monolithic application. The service team was formed for each service as a cross-functional and autonomous team, and team was responsible for all activities that was needed to develop and operate the service. DevOps engineer was embedded in the service team to collaborate with the developers to develop and operate the infrastructure. Our expectation here was that DevOps engineers set up the infrastructure and validate it was working and move on to next service. But the reality did not go as expected. We found that DevOps engineer had to continuously modify the infrastructure as the service was and is constantly adding and refining features. DevOps also had to do measurements and data collections against major events like the launch of AAA titles, such as Smash Brothers and Splatoon. There's also events like Nintendo Direct, where many new titles are launched in available now style. And we also have a holiday season, where many new Nintendo Switches are connected to the network. Developers and DevOps engineers make careful preparations for this kind of events, such as capacity planning and scale out in advance. And under these circumstances, the DevOps engineers were effectively permanently embedded to the service, and we could not transition them to a new project. And as the number of microservices grew, it was difficult for us to maintain this scheme due to our limited number of DevOps engineers. In order to scale the development capabilities, it was considered essential to expand the developers' work areas and to bring the self-service capabilities. But we couldn't simply ask developers to do DevOps, because we would have compliance problems and would only increase the burden of the developers. So we thought about ways to reduce the cognitive load of the developers. This discussion of team structure and human sustainability and scaling started in 2020. And over 3 years, we have built this effort into what we call platform engineering. So let's get into what our platform engineering looks like. With our constraints on DevOps engineers not scaling as quickly as the microservices, We aim to streamline development while reducing the cognitive load of developers. Our plan was to increase the self-service abilities of the developers and to reduce the amount of effort. And platform engineering in general is building a set of tools and practices provided as internal developer platform. This internal developer platform is in turn provided to the developers to develop and operate the application and infrastructures. And in theory, we would have a dedicated platform engineers, but Nintendo eShop system development team currently does not have a person filling that role. And I'll explain why this in a moment. In the next slide, I will talk about what kind of platform engineering we are working on. So, our first step is to define the component that will enable the developers to self-service the development and the operation of application and infrastructure. For example, we have an application framework, container orchestrator, API gateway, and so on. Next, a working group consisting of developers and DevOps engineers are formed for each component. The output of the working group varies depending on the component. The team works on Git repository, produces a template for the new application development. A Terraform module is used for self-service infrastructure development. And application library is a cross-cutting concerns when developing the applications. Other outputs include CI/CD environment and sidecar container for observabilities, and so on. The working group provides the outputs as products to the service team. The service team uses these IDP components where developers take initiative in the development and deployment of applications, as well as developing infrastructures. Because each developer may have a different level of proficiency in infrastructure development, we have DevOps engineers join the service team as needed. And in Nintendo eShop development, each service has its own AWS account. One of the reasons for creating an independent AWS account is that the scale of the Nintendo eShop is quite large, and it is necessary to prepare many server environments for various purposes. To give you an idea, there is a server environment for Nintendo SDK development and other for development of network services and internal QA processes and more. With so many server environments, we would contend with the AWS resource limitations if we are to operate within a single AWS account. By having these independent AWS accounts, we can increase the resource independence between the services and also facilitate self-service and also minimize the impact of any mistakes. So these are the key points of our developed platform engineering. The reason why we did not create a dedicated platform engineering team is partly due to our organizational constraints. But at the same time, we feel that the lack of dedicated team has actually enabled us to create a lightweight platform that is sufficient for our needs. And by having the developers participate in the IDP component discussion, we feel there's an advantage in being able to keep strong relevance to that a developer's perspective. We have defined components that are necessary for self-service and productivity and maintainabilities that work for developers. If we had a dedicated platform engineers, we could have created a more rich and functional internal developer platform and portal. But we feel that our focus should not be on the IDP itself, but on the services that are built using the IDP. So at this point, we are happy with our approach. Rather than creating a rich IDP that covers all the development use cases, we want to provide a developer experience that allows the developers to have discretions. And we want to place an emphasis on that. So next, I'll talk about the nuts and bolts of our IDP. One of the key components is the container orchestrator. We have conducted a proof of concept on Amazon EKS and Amazon ECS, and decided to adopt Amazon ECS. So here's why. First, we were aware that we lacked a team or a member who could manage the platform in a full-time basis. So if we are used to use EKS, it will be a multi-tenant cluster on a single AWS account shared by multiple services. So we concluded that we will be needing a dedicated team to manage the cluster. Of course, it's possible to adopt multi-account, multi-cluster configuration, but that will place a heavy burden on the team to update the cluster once every 3 months. On the other hand, ECS with target type does not require cluster management, and we could eliminate the need for a team to manage the platform. With ECS, the developers who are not familiar with Kubernetes can build and deploy applications on containers. And thanks to the managed cluster of ECS, the DevOps engineers can support the service team as SREs rather than having to manage and operate the common infrastructures. So with each team, the second reason is that to bring self-service capabilities, we want to create a dedicated AWS account for each service. With each team having their own AWS account, they can take ownership of the product, including the infrastructure. Furthermore, the separation of services by AWS account simplified the authority management and psychologically made it easier for the developers to use AWS, and also increased their interest in the infrastructures. So when we think about adopting ECS in a cross-account and cross-VPC environment, how to interconnect the microservice is an issue we have to tackle. Currently, we implement all the traffic controls such as rate limiting, authentication, authorization, and monitoring of traffic between the services. But again, our goal is self-service and reduced amount of effort. So it would be ideal if we had AWS take care of this. That is why we look forward to the future enhancement of Amazon ECS, which is an integration of Amazon ECS Service Connect and VPC Lattice. When integrated, first we connect the cross-account, cross-VPC services by VPC Lattice. And note that when connecting the services, we directly specify ECS service as a target of VPC Lattice. As of now, only IP address or ALB can be specified as a target of VPC lattice. But when we can specify ECS service as a target of VPC lattice, we can omit the application ALB between the services. We believe this will simplify the interconnection between the services and further push the self-service capabilities of our developer platform. Also, ECS Service Connect will allow us to collect the matrix of traffic between the services, which leads to higher observabilities. The Service Connect proxy, which is a sidecar of ECS Service Connect, runs on IAM-based authentication, and the VPC lattice auth policy authorizes the request. This integration of ECS Service Connect and VPC lattice is already on the container roadmap, so we're expecting to be implemented in the near future. So, in the previous slides, I mentioned that we are creating a dedicated AWS account for each service to push the self-service capabilities. This means that we have to create many AWS accounts as the number of microservices grows. To reduce the cost of creating new accounts and to ensure the certain level of security, we have adopted AWS organizations. At the very beginning of the new microservice project, a service team requests to the account administrator for a new account. The administrator then triggers a workflow to create a new account via Create Account API and apply same security policy as other accounts. For accounts under organizations, the service control policy is applied to prohibit operations such as disabling the security-related services. In addition, all account trails are aggregated to the administrative accounts via CloudTrail. And from the aggregated logs, we detect any operations that may be problematic. Security Hub and Guard Duties also monitor all accounts for security problems and notify the person in charge of the account as needed. So, until now, we have been discussing about the microservice and platform engineering in abstract. So, let me grab my talk and the successful use case. The microservice introduced here dynamically checks the user's digital assets when a user launches a game title on a game console. So by design, this service will be heavily accessed in a short period of time on the launch day of major titles. Everyone wants to play a game as soon as possible on the launch day, right? So to achieve the availability and the scalability to handle this, we have decided to develop this functionality as an independent microservice. The architecture is to run application on ECS Fargate, use DynamoDB as storage, and use Cloud HSM for some DRM-related processes. The service was developed and operated by developers using our IDP components in a self-service manner. During the recent launch of Legends of Zelda: Tears of the Kingdom, developers were able to prepare for the load in a self-service manner based on the sales forecast and actual pre-order numbers. For example, Terraform TF file was modified to scale out ECS tasks and Cloud HSM instances. DynamoDB capacity mode was changed to on-demand mode to accommodate the unpredictable traffic. As for the capacity mode, we usually use provision mode, which is optimized for our daily predictable traffic. With the launch of Tears of the Kingdom, in a matter of minutes, the traffic was several times higher than normal. But thanks to the proactive measures taken by the developers, all access were handled without any problems and did not interfere with the users' gaming experiences. Everyone was able to play the new Zelda at launch. So this is a successful use case of our self-service by microservice and platform engineering. We're hoping to bring this kind of developer experiences more widely available. So lastly, I would like to talk about the e-commerce API platform. One of the recent trends in the Nintendo eShop system is the increasing use of e-commerce functionalities in the customer touchpoints other than Nintendo eShop. For example, we have My Nintendo Store, which is an e-commerce site for PCs and other browsers. And we have year-in-review sites and mobile apps. This means that the chance of developers outside Nintendo eShop using the e-commerce functionalities are increasing. And not all developers are familiar with our e-commerce APIs. So to support various use cases and various developers, we are pursuing a strategy of building an e-commerce API platform. So to integrate what I have been talking about as 3 modernization strategies, we are building valuable functions as microservices on top of developer platform that is established through platform engineering, and release those functionalities in a unified and easy-to-use manner as API platform. And as a key component of the API platform, we are operating API Gateway. We have introduced a Kong OSS as an implementation of the API Gateway to centralize the management of requests. By centralizing the request management, we can properly manage which client is using which API for how often. In addition to centralize the management, the API Gateway serves as a protection of upstream microservice from the external accesses. The API Gateway's features include authentication and authorization, rate limiting, and circuit breakers. And some of the features we customized the Kong's default features. Like other microservices, Kong is built and deployed on ECS to simplify its operation. So through the API Gateway, we are hoping to support smooth communication between the microservice developers and API platform users. To do so, we have built a dashboard to visualize the API usage. We can grasp who is using which API for how often in real time. Error rates and other metrics can also be grasped, which allows us to detect any failures. This enables the API users and the platform developers to communicate over the necessary capacity of each API, and also to understand which API user is affected when the API specification needs to be changed. And we have also built an API catalog using the Swagger UI on our in-house wiki. Through this catalog, the developers of various services that wish to use our e-commerce functionalities can easily discover and try out the e-commerce APIs. So lastly, I would like to introduce one of the tips of when operating the Kong gateway. When operating Kong gateway in an environment where we have many server environments and microservices, we need an efficient way to manage the configurations. We use the official tool provided by Kong called Dec to manage the configuration by JSON files. But as there are many server environments and microservices, directly writing the JSON files will increase the management costs. So we needed another solution to manage the difference between the environment and microservice in a dry and efficient manner. To achieve this, we have introduced OSS code JSONnet. JSONnet is a template language to generating JSON files. And thanks to its simple language specifications, it was very easy to implement. When we push the JSONnet code to GitHub Enterprise, GitHub Actions builds the JSONnet files and generates JSON files for each server environment or microservices, and reflect them to Kong via Dec tool. The JSONnet allows us to manage the API gateway efficiently. So let me wrap up my presentation by summarizing and emphasizing the key takeaways. At the beginning, I have introduced the transition and the challenge of Nintendo eShop system. As an approach to the challenge, microservice and platform engineering were introduced. We believe that microservice fits for us to achieve long-term maintainability and to embrace new technologies. And to mitigate some of the pain points of microservices, we are working on platform engineering. Our approach was to let developers and DevOps engineers collaborate to build efficient and developer-friendly internal developer platform. Then I have introduced some of the components of our internal developer platform. We believe that Amazon ECS fits well for our self-service and independent AWS account environment. And the future prospects of ECS could further push the self-service capabilities of our developer platform. So we are expecting for that. And lastly, I have introduced the e-commerce API platform concept to support various use cases of our e-commerce functionalities. And as a key component of our API platform, I have introduced the API gateway that we are operating. The modernization of Nintendo eShop system is still ongoing, and we will continue pursuing the better developer experience and, of course, better user experiences based on the approaches I have introduced today. And that's all for our presentation, and thank you very much for your attention.